Okay, so introduction to eigenvalues and eigenvectors. So in this lecture, we will, find my pen, we will look at the definition of eigenvalues and eigenvectors, geometric meaning, linear independence, how to find them. So the definition of eigenvalues and eigenvectors is right there. If we have a 2x2 matrix, and you can do this with higher order matrix, and we'll look at that later in the semester. For a 2x2 matrix, A, B, C, D, lambda is some number and V a vector. If you get M times V equals lambda times V, remember that this is a matrix and that's a number, then lambda is called an eigenvalue and V is an eigenvector associated to lambda. So first thing is sort of, let's start thinking about what these mean a little bit. Can we verify if this is our matrix? Let us verify that lambda 1 W is in fact an eigenvalue eigenvector pair. So MW equals lambda W is what we want to show. So the left-hand side is M times W, which is -4 -2 3 3 times 1 minus 3. So it'd be -4 times -1 times 1, which is -4, -2 times 3 is 6, 3 times 1 is 3, 3 times -3 is -9. And that's 6 minus 4 is 2, -9 minus 3 is -6. The right-hand side should be 2 times W, which is 1 minus 3, which is 2 minus 6. And they're equal to each other. So we can check that they're a eigenvalue eigenvector pair by multiplying the matrix times the vector, multiply the vector times the eigenvalue, and you should get the same thing. So any multiple of W is also an eigenvector. So if we basically do the same thing, let K be a number, in general, I won't do it with this particular example, but in general, we have MW equals lambda W. That's what it means to be an eigenvector, eigenvalue pair. Then M times a multiple of W equals lambda times KW. Oh, no, actually, I don't want to do that just yet. Then that's the conclusion I want to draw. M times KW equals K times MW, because we know we can move scalars out of matrix multiplication. But we know that MW is equal to lambda W. And lambda and K are just numbers, so we can switch them around. So that means M times KW is lambda times KW. So the entire span of W, right? That entire line that W defines this is all eigenvectors, right? So we actually have infinitely many eigenvectors because you can always scale an eigenvector and it still remains an eigenvector. So what is the geometric meaning of eigenvalue and eigenvector? We can think about multiplication as by M as a function from R2 to R2. So if we have our matrix M, we'll take the example from the first one, which is -4 -2, 3 3. And we know that lambda equals 2, W equal to 1 minus 3. 1 minus 3 is an eigenvector eigenvalue pair. So what does that mean geometrically? So we have our plane, usually with the I and J coordinates, which actually aren't important here, but we usually put them in anyway. And that gets mapped over to my codomain. And MI and MJ get mapped wherever they go. So W is -1, and then up 1, 2, 3. So that's my vector W. What happens over in the codomain, we know that MW is just 2 times W, which is minus 2, 6. So 1, 2, 1, 2, 3, 4, 5, 6. So what we have is a weird thing in that we're thinking of the domain and the codomain as being related to each other. At least we can say what the same line is. W and MW both lie along the same line. They both point in the same direction. So often when we're thinking about matrix multiplication by square matrices, we blur the distinction a little bit between the domain and the codomain. This was the domain. And we say, okay, well, if we put them both on one graph, then W is like this, and MW is like that. So an eigenvector is a vector that is not, that doesn't have its direction changed by the matrix multiplication. Or you can think of it as this line that W lies along gets mapped to itself by the function M. And that's an important thing in mathematics. We're always looking for things that actually don't change, because then that gives you a way to sort of grab hold onto functions a little bit. And this is an important aspect of that. Suppose we have two different eigenvalues. So lambda 2 equals minus 3. But this is the same matrix that we had up in example 1. So show that lambda 2 equals minus 3, v equals 2 minus 1 is an eigenvector, eigenvalue eigenvector pair. That means we want mv equal to lambda v. Left-hand side, in this case, minus 4 minus 2, 3, 3, times 2 minus 1. And what is that equal to? Minus 4 times 2 is minus 8. Minus 2 times minus 1 is plus 2. 3 times 2 is 6. 3 times minus 1 is minus 3. And we get minus 6, 3. If I factor out the minus 3, it's 2 minus 3 times 2 minus 1. And that's the right-hand side, right? That's lambda times v. So we've got, this matrix has got two eigenvalues. And one is 2 minus 1, and one is the other pair that we had. And the other pair we had was lambda equals 2, and W above was 1 minus 3, right? So there's one eigenvalue eigenvector pair for our matrix. There's the other pair. So from previous examples, we can see that from this example, we can see that lambda 1 equals 2 and lambda 2 equals minus 3. These two vectors are linearly independent. It's pretty easy to see that 2 minus 1 is not a multiple of 1 minus 3, but this is actually true in general. So suppose we have a square matrix and lambda 1 v1, lambda 2 v2 are two eigenvalue eigenvector pairs where lambda 1 does not equal lambda 2. So we're going to show that v1 and v2 are linearly independent. So to show k1 equals 0, k2 equals 0 should be the only solution to this equation for them to be linearly independent. What do we know? MV1 equals lambda 1 V1, because that's what it means to be an eigenvalue eigenvector pair. And MV2 equals lambda 2 V2, because that's what it means to be an eigenvalue eigenvector pair. So I'll call this here equation 1. So step 1, first multiply equation 1 by lambda 1. That gives me K1 lambda 1 V1 plus K2 lambda 1 V2. Right, multiply the left-hand side, and we put it as equal to 0. We want that to be equal to 0. We need to show that, oh, that's okay. It is equal to 0. We want to show that the only way that can be is that K1 and K2 are equal to 0. Second, multiply equation 1 by M. M times K1 V1 plus K2 V2 equals M times 0. And that's actually the 0 vector over on the right side. So using the various properties we know about matrix multiplication, we can break that apart. We know matrix times 0 is 0. K1 can come out. And now MV1 is lambda 1 V1. And MV2 is lambda 2 V2. So we have these two equations. And we want to show the only way we can solve these equations is if K1 and K2 are both equal to 0. But notice that they have the same term in common. So, and they're both equal to 0. So if we set the left-hand side here equal to the left-hand side here, what do we get? We get K2 lambda 1 V2 equals K2 lambda 2 V2. Now we would like to do some kind of cancellation here, but we have to be a little bit careful about it. So instead of canceling, because there's vectors and we're not coming around. So instead of canceling, we're going to move this all to one side. Then we get K2 times V2 times lambda 1 minus lambda 2 equals 0. So subtract this from both sides, and then we pull out the K2 V2. So lambda 1 is not equal to lambda 2, so that means this part is 0. V2 is an eigenvector, so V2 is not equal to 0. So the only way this can be equal to 0 is K2 must be equal to 0. And that forces K1 equal to be 0. Great. So eigenvectors that belong to different eigenvalues are automatically linearly independent, and we don't have to check that. So how do we go about finding eigenvalues? Right? Up above, we just sort of said, here are eigenvalues, but here we want to see how to find them. So the defining equation for eigenvalue eigenvector pairs is MV equals lambda V. Great, and you want to solve that for both V and lambda, they're both kind of unknown. A very useful note, if we set V to have components, we'll call them V1 and V2, then multiplying by lambda just multiplies both components by lambda. But also, lambda times I2 times V equals, well, remember that I2 is the identity matrix. With ones down the main diagonal and zeros elsewhere. I can multiply lambda into the identity matrix to get this. Oh, these are not vectors. They shouldn't have arrows on them. V1, V2. Then you get lambda times V1 plus 0 times V2, 0 times V1, lambda times V2 for the second one. These are equal. That makes me happy because I can rewrite my defining equation like this, which doesn't look particularly important, but is actually very slick because now I can subtract that from both sides. And now this is a matrix and this is a matrix, and that's just a vector, so I can subtract out, factor out the matrices. Yay. So that should be an arrow. So what do we got there? We've got that to find the eigenvalues, we need to have a solution, non-zero solution we need a non-zero V as a solution. What we saw from the last video is that a matrix, I've already used M, so I use a different letter, N, and V equals 0, has more than one solution. Only when the determinant of N is equal to 0. So that tells me how to solve this, right? How to find eigenvalues. Take this matrix, M minus lambda I2, set it equal to 0, solve for lambda. And that will give me my eigenvalues. So the determinant we want is of the vector -4, -2, 3, 3, minus lambda times I2, as we pointed up here, is just lambda 0, 0, lambda. And that becomes the determinant of -4 minus lambda, 3, 3 minus lambda, and then -2. Great. Remember that determinant is this one times this one minus this one times that one. So it should be -4 minus lambda, 3 minus lambda, minus 6. If we multiply all this out, what do we get? Well, we've got a lambda squared, a +4 lambda, a -3 lambda, a -12, and a +6. And we can factor that. We get lambda plus blah, 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 lambda plus 3 and lambda -2. So our eigenvalues are lambda equals -3, lambda equals 2. We'll call them lambda 1 and lambda 2. And we already knew that because we've actually shown that lambda 2 equals -3, and lambda 1 equals 2 are the two eigenvalues. Notice that when you take the determinant, we get a quadratic equation that we want to set equal to 0. And this is the characteristic equation. We have seen this before. We will show the connection to second order equations next week, I think. So eigenvalues, lambda equals -3, lambda equals 2, so lambda squared plus lambda -6 equals 0 is the characteristic equation, and its roots are -3 and 2. So here's the procedure for finding eigenvalues. If M is A, B, C, D, set up this matrix, A minus lambda, B, C, D minus lambda, set its determinant to 0 and solve for lambda. So here's a matrix. Find the determinant. To find the eigenvalues, we take the determinant of -2 minus lambda, 5, 2 minus lambda, -1. And that's -2 minus lambda times 2 minus lambda. So that's these two. And then minus the cross. And that's going to be -5. So that's going to be actually +5. If we multiply this out, what do we get? We get -4 plus 2 lambda minus 2 lambda plus lambda squared plus 5. That should be a -4. And so we end up with lambda squared plus 1. And we set that equal to 0 and solve for lambda. Hopefully, that shouldn't come as a total shock, right? Because characteristic equations, sometimes our characteristic equations for 2x2 matrices are quadratics, and sometimes you get imaginary roots. So here we are, we have imaginary eigenvalues. Lambda 1 equals I, lambda 2 equals -I. Our geometric understanding of this is a little bit tricky. We'll see this, an explanation of what the eigenvalues and eigenvectors mean when they're complex a little bit later when we start dealing with the systems of equations, of differential equations. And what's the third option, of course, if you have quadratic equations? The first example we did had 2 real eigenvalues. The second example we did had 2 complex eigenvalues. What's the third one? Well, that'll be a repeated root. So how do we find the eigenvalues? You take the matrix 10 minus lambda minus 4 minus 2 minus lambda 9, and we set that equal to 0, solve for lambda. So that's 10 minus lambda times -2 minus lambda plus 36, right? Because it's -9 times -4. So we get -20 plus 2 lambda -10 lambda plus 36 plus lambda squared plus 36. So it's lambda squared -8 lambda plus 16. And here we just have one eigenvalue because there's only one root. There's a number of different ways to handle this. We'll see. This only gives us one eigenvector because we get it from the eigenvalue, and we'll see how to handle the lack of a second eigenvector again when we do systems of equations. So how to find eigenvectors? So eigenvectors are solutions to this equation once we've figured out where lambda is. And so we are looking for the solution to this equation, right? MV minus lambda V becomes M minus lambda I2 V equals 0, and that's what this equation is. And the solutions to this equation should give us the eigenvectors. And there'll be infinitely many because any multiple of an eigenvector is an eigenvector. The eigenvalues should mean that if there's infinitely many solutions, we should get a row of zeros. Or in other words, one of these rows should be a multiple of another. And it's a very useful check on things. So in example 6, we found that the eigenvalues, oh, I hope I didn't make that mistake in all of these things. Eigenvalues of -4, -2, 3, 3 is lambda equal 1 equals -3, lambda 2 equals 2. So lambda 1 equals -3 case, find the eigenvector. So we take -4 minus -3, 3, 3 minus -3 minus 2 times v1, v2 equals 0, 0. And we want to solve that. So we want to be careful here. We have -4 plus 3, which is -1, -2, 3, 3 minus -3 is 6. So as a check, are the rows multiples of each other? Yep, if I multiply the top row by -3, I get the bottom row. So good, we're on our way. So v1, v2 equals 0, 0. So as equations, this would be -1 v1 -2 v2 equals 0, and 3 v1 plus 6 v2 equals 0. But we can use either one of those equations to figure out a vector v1, v2, because they're the same equation, just multiplied by each other. So I'll deal with this one, and I'll set v1 equal to 1 and v2 equal to -2. So we get an eigenvector, which I think up above I call w, 1 minus 2. So I now have an eigenvalue, eigenvector pair. And for lambda 2 equals 2, we can do the same thing. We take our matrix, -4, and we subtract off the eigenvalue from the main diagonal. And we solve this. So we get -6, -2, 3, 1. We want to apply our check. 3 times -2 is -6. 1 times -2 is -2. So the rows are multiples of each other, so that works. It is an eigenvalue. So then we'll take the bottom equation, which is 3v1 plus v2 equals 0. We set v2 equal to, if I set v1 equal to 1, then v2 would be equal to -3. And that gives me an eigenvector. And so now I have an eigenvalue, eigenvector pair. Of course, any multiple of this is also an eigenvector, and it would be paired with that eigenvalue. I don't know why this is trailing a little dot there. Any multiple of this w is also an eigenvector associated with lambda 1 equals -3. Great. So eigenvalues of this matrix were plus minus I. So what are the corresponding eigenvectors? Well, we set up the equation for finding the eigenvectors. -2, lambda 1 equals I case. -2 minus I, -1, 5, 2 minus I, v1, v2, 0, 0. Our check here is a little bit difficult because we have these imaginary numbers, but we know that -1 times -2 minus I equals 2 minus I. So if I want to do a check that the bottom row is something times the top row, well, the something has to be this, because -1 times this is 2 minus I. So if I multiply the -1 by -2 minus the quantity 2 minus I get this. If I take -2 minus I and I multiply by the quantity -2 minus I, do I get 5? So I can take this minus sign, multiply it into here. I get 2 plus I times 2 minus I. And these are conjugates, so that gives me 4 minus I squared. 4 minus -1, because I squared is -1, which equals 5. Great. So in fact, the bottom row is a multiple of the top row, but it's a multiple involving a complex number. Okay, so we'll take one of these equations to define my eigenvectors. I'll take the bottom one because the top one just has too many minus signs in it for my liking. So 5v1 plus 2 minus I v2 equals 0. So I can take v2 equal to 5. Actually make v2 equal to -5, and then that would make v1 equal to 2 minus I. Right? Because that makes that 5 times 2 minus I plus -5 times 2 minus I, and that is equal to 0. So what vector do I get? Well, vector 1, 2 minus I, v2 equals -5, -5. And I can break that up actually. Like that. So this is 2 minus 5. This is technically plus 0I. Then I get minus I, which is -1 times 0. So how do I get the calculation? How do I get the eigenvector for minus I? Well, we'll just go through this whole calculation and switch the signs on i's forever. And you get that your eigenvector, we'll call it v2, is going to be 2 minus 5 minus I -1, 0. So this is called the real part. This is called the imaginary part. The vector itself, not including the I. And those will be very useful when it comes to solving systems of differential equations that have complex eigenvalues. But the procedure is just the same. I is a number. It works the same as anything else. It's just got a little quirk that I squared equals -1. And so finally, here's an eigenvalue. Can we find a corresponding eigenvector? Well, same deal. We take the matrix 10 -4, -4, 9, -2, -4. So we subtract the eigenvalue off the diagonal. v1, v2 equals 0, 0. And we want to solve this for v1, v2. So I get 6, 9, -4, -6. We can do a little check. Is the top row a multiple of the bottom row? And the answer is, yeah, it is. The bottom row times -1.5 will give you the top row. So we can take either one of these. Again, I don't like minus signs, so I'll take the top row. 6v1 plus 9v2 equals 0. You could take -4v1 minus 6v2 equals 0. I'll define everything by 3. And I'll take v1 equal to 3 and v2 equal to -2, right? So if you take the number to be the other coefficient, you can get 0 pretty quickly. So this would be 6 minus 6. And there's our eigenvector that goes with this particular eigenvalue. Great. So finally, a summary. If M is a matrix, A, B, C, D, and this can be extended to higher dimensions, and we'll see that later, but this is what we need for dealing with systems of differential equations. So take this matrix where you subtract lambda from the diagonal, take its determinant, set it equals 0, solve for lambda, you get a quadratic equation, so we'll get the usual collection of possibilities. Now, for each eigenvalue you get, plug it in for lambda and solve this equation for v, and that will give you an infinitely many vectors to choose from. Choose one that's got, that's relatively nice. I always try to avoid fractions and minus signs generally when I try to find my eigenvalues and eigenvectors.